Good morning, good afternoon, or good evening. We are back on the Step 3 2024 paper, and we're now on to question 6. Hope you've already had a strong go at this yourself. And now you're looking either for the alternative thought processes that will get you through the question, or you're looking for a hint for you to take the question that little bit further. As with all of these questions, they are basically blind to me. I've not done any of these questions before. I am trying to have this as a process for you to see how one would tackle these in a first attempt. So I haven't gone and found solutions beforehand or done any scrap work beforehand. Let's jump straight into this question. We have a particle moving in two-dimensional space with coordinates x and y, and then the third variable t is going to be our time component. Very common way that physicists start to model motion. And we also have u being a function of time. And we've been told that at a particular time, the particle has position x0, y0. And we've been told to think about a very special combination. We've been told to think about dx by dt minus dy by dt, and then showing something about the initial conditions after that. So let's do exactly that. We have the dx by dt, which from now on I'm going to call x dot. That's the common abbreviation for a derivative with respect to time, is as given, and then y dot is also given. And the question told us to consider x dot minus y dot. So I'm going to subtract these two things. And you can kind of see the whole point of this actually is to get rid of this u thing at the end. It's going to be minus 2x plus 2y. There's no u's, and I'm going to do something a little bit silly here because I can see an x minus y in two places. So this side, if you think about the rules of differentiation, is the derivative of x minus y, whereas on this side it's minus 2 lots of x minus y. So I could actually solve this differential equation if I wished to. And it looks like I might want to. One way to think about this condition here is that the x minus y is 0 at the origin. The difference between these, if they're equal to each other, would be equal to 0. So let's try it. Noting the general solution for such equations is x minus y equals something e to the negative 2 t. That's just using the fact that if you have dy by dt equals ky, then that's really 1 over y over here, which will become ln y equals kt, or y plus c. Yeah, so just a little bit of a mental check there that this differential equation does exactly solve as I thought it did, and yes it does. So we've now been told, by considering that, show that if the particle is at the origin at some time t greater than 0, so at a time t greater than 0, we are saying that x equals y equals 0. Well, that's going to mean that a e to the negative 2t equals 0, but e to the power can never be 0, which means a equals 0, i.e. x is equal to y, or x minus y equals 0 at all times. So So in particular, I'm being extra, being a bit extra with the way I'm writing this. In particular, at t equals 0, x naught equals y naught. So actually, this result is a lot stronger than what they seem to be wanting us to show, which is a little worrying. We've shown not only are they the same at the beginning, they're the same always. So if this particle ever hits the origin, then everything collapses and the x and y's are the same, which is kind of the behavior that the difference here is 2, the difference here is 2. It's still a little worrying that how strong this result is, and if actually we didn't even have this equal to 0 condition, if it was just that x equals y at any point, then we'd get the same condition, we'll get the same result. So that's a little bit worrying and something to have in our mind as we continue to model. Part B. So now we're going the other way. Given that x naught equals y naught, find a constant value of u that ensures the particle is at the origin at some given time. So we're now saying we start at the same place, and we want to find a value of u that ensures when, and it's a constant value this time. So what we have in the first part, does the first part still hold? So we could still create this equation here. We still create the solution. Now if we put t equals 0 in, we know that x naught equals y naught, so this side would equal 0 and the other side would equal a, so the a would still be equal to 0. So we do have the same kind of result. So from I part A, this is saying that x is equal to y again. So now, trying to debate the best way to do this, probably the best way is just to solve one of these original equations. So that means that the first equation is going to collapse to x dot equals 2x, because the x and y are the same. I can collect them together, and we're saying a constant value of u, so this is plus u. And now I'll quite like to solve this differential equation. And this is our integrating factor-esque attempt. So this side we can write as the derivative of x e to the negative 2t. If I move that 2x over, that will equal u e to the negative 2t. I've multiplied it through by the integrating factor e to the negative 2t. I'm just going to quickly double check if I do chain rule, product rule this side out. I'm going to get the x dot with the e, and then when I multiply the derivative of the e term, I'm getting a minus 2x, which is exactly what I want. So this is going to be equals, integrate that, so it's going to be minus a half u e to the negative 2t, so x and y, and really there's a plus c on this. I'm multiplying through now, so this is going to be negative a half u plus c e to the negative 2t. Find a value of u that ensures the particles are at the origin at that capital T. So I need to find this constant c first. So when t equals 0, x equals x naught, which is as so. So that means this c can be written as x naught plus a half u. So therefore the function x Just debating whether I want to do any clever factorizing to make this look nicer, is the c e to the power minus that. And I would like this to be at the origin. So when t equals capital T, x equals 0, so that's going to be that the half u, which I'm going to put onto the other side, x naught plus a half u e to the negative 2 capital T now. And I want to rearrange this to make u equals. So if I bring stuff over, this side could be 1 minus e to the minus 2t equals x naught e to the minus 2t. I've just brought the u term over and stuck it in a bracket. So I want to say now that u equals multiplying through by the 2 and dividing through by the e, and the one last thing I'm going to do is just get rid of the negative powers by timesing through by e to the 2t. That destroys the e to the minus 2t's quite nicely. So u can be this constant, and as x equals y, with this u, y at time capital T is also equal to 0, i.e. the particle is at the origin. Exactly what we wanted from this part of the question. Apologies, a little sneeze break. Okay, so part 2 now of the question. We're now going into 3D space, and we therefore have a dx by dt, dy by dt, and dz by dt. I'm just looking straight away if there's any patterns amongst the coefficients. In the same way up in the top, we had a pattern where the x is added, or the x is subtracted and the y subtracted to give the same value. If I add, potentially something clever is going to happen. But then the z's don't look like they line up with how the x's do. So maybe, maybe not. Three-dimensional space given by those equations, where u is a function of time. At time 0, we're starting at some fixed starting point. Show that if the particle is at the origin at some point, it is necessary that y naught is the mean of x naught and z naught. So part part A, we're trying to show we're required to prove that y naught is half x naught plus z naught, which is the same as saying x naught, I'm going to times through by 2 and put everything on the same side, this thing is equal to 0. Reason I've done that, because that feels very much like the condition we got here with x minus y being equal to something. So I quite would like to create an equation that looks like this. So I'm going to consider the derivative of this style of expression and hope that that's the expression where all the coefficients do the beautiful stuff. So I'm going to consider x minus 2y plus z, and I want the derivative of that whole thing, d by dt, of that entire thing, which, using those equations, is dx by dt, which is 4y minus 5z plus u, minus 2 lots of x minus 2z plus u, plus 1 copy of the x minus 2u plus u. So let's see what this simplifies down to. We've got minus 2x plus an x, that's a minus x. You've got 4y minus 2y, that's plus 2y. We've got 5z, we're adding 4z, that's a minus z. And the u's, again, have cancelled out perfectly. And even better than all that, this is exactly negative of the expression that we were starting with in the derivative. So once again, this is going to solve as a differential equation really beautifully. So this expression is equal to something e to the negative t. Previously we had the negative 2 because there was a 2 in that spot. There isn't on this one. And then we've been told, show that if the particle is at the origin for some value of t greater than 0. So if x equals y equals z equals 0 at some t, that's going to mean that this a has to be 0. The left-hand side is 0. The right-hand side is a multiplied by something that can never be 0, which means that x minus 2y plus z equals 0 for all time, which in particular means at t equals 0, x naught minus 2y naught plus z naught equals 0, so y naught equals the mean of those as required. And you can kind of see the thought process at the beginning of what am I trying to do to motivate what I actually ended up doing. And then this last bit here is exactly this logic in the opposite order to get to what I actually wanted. I never really want to meet in the middle in a show that question. I'd much prefer to get from the beginning to the end. Okay, so that's that part done. So part B of this question, show further that if the particle is at the origin at some time, then it's necessary that all of these are actually equal. So we've shown that y is the mean of x naught and y naught, but we actually want to show that they're all the same at the origin. So I could try and do a trick like I did in part A of part I and consider x dot minus y dot. But actually, if I look at this one here and this one here, I can cancel the x's and the u's out in one go. So I'm going to do that. And then if I can show that y naught is equal to z naught, but y naught is the average of x naught and y naught and z naught, then I'm actually sorted. So let's consider the derivative of y minus z, which is equal to, and if I subtract those two equations, the x's cancel, the u's cancel, I'm going to be left with minus 2 y minus z. Just double check that the signs have worked fine. I'm expecting, nope, the signs are wrong there, so is this just a positive 2? I'm expecting to have a minus 2z, which I've now got, and a positive 2y. Nice. Which means that the y minus z is equal to some constant times e to the 2t. But then if y naught, if y equals z for some t, that's going to mean that the b has to equal 0, i.e. that y equals z for all t, which in particular means that y naught equals z naught, and then combined with y naught equals a half x naught plus z naught. This implies, and you can do the algebra properly here, and it would come out exactly as you expect. This implies that x naught equals y naught equals z naught as required. And I'm a little worried that what we're proving is actually a lot stronger, that these functions are the same at all times, not just at the origin, which is slightly concerning, but that's okay. And then finally, part C, given that they are equal, find a constant value of u that ensures the particle is at the origin at the particular time. So we're now doing the same as part B of the previous part, but now with 3 variables. So now, using part A and B, we have that the functions x equals y equals z, because I have that at this condition here. I still have they are equal for some t. Now we know they're equal when t equals 0. So I can say that the y function is equal to the z function, and similarly we had that same statement there. If the y is equal to the z, then the x has to be equal to them individually as well. So all the functions are the same, so we can collapse any of our functions. So then equation 1 is going to collapse to be x dot equals, the x's and y's are, the y's and the z's are the same, so that's going to be minus x when we collapse all that together, plus u. So the integrating factor this time is just e to the t. So this is x e to the t is going to be equal to u e to the t. Integrating across, putting in an unknown constant. So the function x and y and z are all given by the expression u plus c e to the negative t. At t equals 0, x equals x naught. So x naught equals u plus c, which means the c is x naught minus u. And at a general time then, we have that expression for x. And then we want it to be the origin at time capital T. So at t is capital T, x equals 0. So 0 equals u plus x naught e to the negative minus u e to the negative. I want to solve this for u. So let's throw this over. I probably wanted, well, this u is always going to be negative. I've thrown the u terms over to the left, factorised, so u is going to be equal to, I did pause there for a moment because this thing is always going to be negative. Yes, anything to a negative power is definitely going to be less than 1 over e to the negative t minus 1. So this is going to be, if I times top and bottom, if I fix the negative sign slightly, this is going to be e to the t minus 1. So u is equal to this value. How did I word it the previous time? If it lets me scroll back. So then as x equals y equals z, with this u at time capital T, we are at the origin. So really what's happened here is these differential equations, I'm just trying to think as we're going through this, what's actually going on. These differential equations are not actually in three-dimensional space, because the x-coordinate, the y-coordinate and the z-coordinate are all the same at all times. That's what this condition that we've created each time has given us. So actually this is in one-dimensional space, just at a weird angle that we're maybe not used to. We're coming out as an x equals y equals z style line out of the origin. That question turned out to be relatively pleasant. There weren't any tricks that caught me this time, and hopefully that was quite a useful explanation of this problem, and in particular the weird trick of making up a new variable and actually having a differential equation in a different variable, but it looks like a differential equation that we're very comfortable in playing with, this exponential growth or decay style equation. Hopefully that was useful, and the playlist below has the rest of the questions from this paper. Good luck.